One line of dropout can save you hours of tuning if you apply it the right way. By the end of this video, you will understand when dropout helps, how to add it without breaking inference, and how to judge if it actually improved your model on a simple Python baseline. I'm Professor Pi, teaching AI foundations with simple Python. Dropout often shows up when a model fits training data too well and then fails on new examples. It is a lightweight regularizer that people reach for when models memorize noise instead of learning signals. In practice, that happens on small to medium data sets, noisy labels, or when a network is larger than the task requires. The payoff is more reliable predictions with little computational overhead. At a high level, Dropout randomly turns off hidden units during training. That forces the network to spread information across many units instead of relying on a few memorizing neurons. Imagine several weak helpers sharing a job instead of a single overloaded expert. That makes the ensemble of subnets more robust at inference. We will build a tiny synthetic regression example so you can see overfitting and then add dropout to measure the effect. The code is short and uses PyTorch. No deep math. You will be able to run this on a laptop and see validation numbers change. Now we create the synthetic dataset and split it for training and validation. This snippet creates a compact synthetic regression set using PyTorch to reveal overfitting risks. The variable x holds evenly spaced inputs, and y adds Gaussian noise to a sine curve, ensuring the target contains signal plus randomness. The call to torch manual seed fixes randomness so results stay repeatable. We then split tensors into training and validation slices, named XTR and XVA with their matching targets. The print shows noise STD, computed as the standard deviation of y minus the clean sine signal, summarizing how much irreducible noise is present. A higher noise standard deviation signals stronger pressure for regularization. Next, we train a small network until it overfits on purpose. This snippet builds a small multi-layer perceptron in PyTorch to intentionally overfit. The sequential model M stacks a linear layer, a ReLU, and a final linear that predicts one value. The Atom optimizer in torch.optim updates weights using mean squared error computed on XTR and YTR. We iterate 200 updates, clearing gradients, backpropagating loss, and stepping the optimizer. After training, TR measures training MSE, while VA measures validation MSE on held-out data, XVA and YVA. The printed gap equals validation minus training loss. A positive value indicates the model fits training better than validation, a classic overfitting signature that we will address next. Now we add dropout into the hidden layer and retrain. This snippet introduces dropout inside a PyTorch sequential model to curb overfitting. The variable MD mirrors the previous architecture, but inserts NN dropout with probability 0.3, randomly zeroing hidden activations during training. Using the Atom optimizer again, we run the same number of updates, which encourages the network to rely on distributed features rather than memorizing noise. We then compute VAD, the validation MSE for the dropout model. The printed gain equals the plain model's validation loss, VA minus VAD. A positive value means dropout improved generalization. Increasing the dropout probability strengthens regularization, but risks underfitting. Decreasing it weakens regularization and may not reduce overfitting. Before we compare behaviors, let us check how dropout behaves during training versus inference. This snippet demonstrates how PyTorch toggles dropout behavior via train and eval. Calling md.train enables nn.dropout to randomly drop units, so repeated forward passes over XVA produce slightly different predictions. We stack them with torch.stack and summarize variability by the mean standard deviation, STR. Switching to md.eval disables dropping, making the model deterministic. New forward passes stacked similarly yield SEV near 0. This check confirms you used the correct runtime mode for training and inference. The printed noise levels show stochastic training time predictions and stable evaluation time outputs, which matters for fair validation and consistent deployment behavior. Now run both trained networks in true inference mode and pick a winner on validation loss. This snippet performs a fair head-to-head evaluation by switching both models to PyTorch eval mode. The variable VND computes validation MSE for the plain MLPM, while VADO measures the dropout model MD using the same held-out set. Because eval mode disables NN.dropout randomness, both metrics reflect true inference behavior rather than training noise. We then select a winner string based on which validation loss is lower. The printed result names the better generalizer and shows the dropout model's validation error, confirming whether regularization delivered a tangible improvement for this small baseline. If you were to map this toy example into a real project, do the same steps with your dataset split and a model sized for your task. The ideas scale. Measure a training to validation gap, add dropout to the parts of the network that overfit, verify train versus eval behavior, and then compare validation metrics under eval mode. Quick recap in 3 crisp points. Dropout randomly disables hidden units during training to reduce co-adaptation. Use dropout when your model shows a clear training versus validation gap, or when you have noisy targets. One caveat: too much dropout can underfit, so tune the dropout probability carefully. Next step, tune the dropout probability and rerun the head-to-head comparison to find the sweet spot for your dataset. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.